तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We will consider a couple of design examples, and as we go along we will see why we take a particular example and how to solve using Verilog code. And see, to start with, we will look into traffic light controller. This is as a result of observation of one of the busiest traffic light junction in Chennai, and I had been observing and passing through that junction and for quite a long time, and result of which is what I have designed here. And so this is the traffic light flow at that particular junction. It's basically you have a main road here, and both directions the traffic flows, and the very first sequence is there will be a green light here, and for both the directions, and there will be red light preventing this traffic flow here. And this is the main road, and it's timed for 45 seconds, and this is exactly what it is in that particular junction. And after 45 seconds elapse, it will go yellow here for both the main. That means green is withdrawn, and the second, that is the second sequence. And in third sequence you have a right turn here, and both ways here, and there will be a red signal preventing this straight traffic flow, and so is the case for the other direction. And naturally there will be a side red in order to prevent this traffic, and once again this will turn into yellow, and that's what it is here. And perhaps they have made a mistake, or I have made a mistake in one of this. Probably this red should have continued here, and I will leave it as an exercise for you to change the code accordingly. That's a very simple exercise. And so all through it is all free left, and that's why I have put it here. And there are further sequences, and in the fourth, this is the fifth sequence here, and this will go red, preventing traffic here, and it will allow the side road traffic to come on. And in the earlier thing, what I have forgotten to mention here, this yellow lights will be on, so also all other yellow lights only for 5 seconds. And once this is for 25 seconds flow, and once again it will go yellow here, and then switch over to the right traffic from this direction. From the side roads, right turn will be allowed. And in this case, so the nomenclature adapted here is M for main, then R for red, G green, then you have Y for yellow, and then RT stands for right, and S having the same meaning as side. and finally once this is allowed, this also will flow for 25 seconds, and once again an yellow light it will have to go through, and naturally withdrawing this side right. This is basically an arrow with a green arrow rather here, and so was the case for the main MRT1, MRT2 earlier shown. And after this sequence, so it will go back to S0 sequence, and it keeps flowing in this sequence perpetually, and or I mean till the COP turns it to blink mode, which is the case in this particular junction. So around 9:30 or 10 I have observed in the night, and it goes blinking, all yellow lights blink here, and this is only to caution the traffic that they will have to be careful, exercise restraint and go carefully, and this is what we are going to look into. So first we will see the code for this. So this is the design. We will see the Verilog code for this design, and it is RTL compliant, as I have been emphasizing all through the course, and the top design module is traffic underscore controller dot v, and so some of which you have already seen the specifications. This controls the traffic lights of a 4-road junction. The timing for the main road traffic is assumed to be 45 seconds, and that for the side road it is 25 seconds. Yellow lights will be on for 5 seconds when they are switched on, and it is a free left traffic, and we have also seen yellow lights flashing when blink control is switched on, and this is for beyond normal traffic hours, and it will flash at the rate of 0.5 Hertz. There is no sanctity for this. Actual traffic junction may have slightly faster thing. I have purposely toned it down so that the lamp life will be better. So you have to see a traffic light controller document. We should always generate a document, and which gives the specification. Instead of the document, what we saw was the PowerPoint presentation earlier, and that may be regarded as the specification document. And test bench for this design is goes by the same name with an extension of test. This is my style of coding and naming the files, and this nomenclature also we have seen. This is the notation used. Main, side, green, red, yellow are all abbreviated in this fashion, right as well. And this is the main road. So here it is called Anna Salai, and there is Venkatnarayan road or some such road. It's Nandanam circle it is called. So I have as far as possible I had put the very same sequence here, and this part of the road, this going towards this side is the main road here. Towards the airport it goes this way, and the other way towards central station it goes to. So this is a main road 2, and we have a side road 1 and side road 2. It is only a nomenclature. It is actually a single road. We, for convenience sake, we are putting numbers here, so that when we come to the actual lamps, we will identify in terms of these numbers. This is a line comment we have seen, and what we are doing is we have basically an FSM realization, a state machine realization, and each of the states is indicated by S0 through S8, and its decimal weight you can say is 0 through 8, and these are all the defined statements that you have. And you notice that we need 45 seconds, 25 seconds, 5 seconds, as well as 1 second timer, 1 or 2 seconds timer. So naturally you need a counter for realizing the same, and we will go into the design of the timers as well. And for that, what we need is we need a time base for any accumulating of count, and if you are to interpret in terms of time. So we should have a time base. Let us say a convenient time base could be 0.1 second, and you can trigger based upon this other counters and run to the precise 45 second, etc. So in this case, this time base is programmed for 9. This count take place 0, 1, 2 right up to 9. That means we have totally 10 clock cycles influencing this counter, and so is the case with all other counters. and this is 22D9 is used only for simulation purposes, I have mentioned here, because what we need is if you are to configure this with a frequency of operation at 40 megahertz, this is the clock frequency, system clock, and then what we need is quite a big number to be loaded in this particular time base, this particular counter. This is counter 1, and we need a very high value to be loaded. For example, this is equivalent to 4 million, and 4 million 40 megahertz. So that means 10 hertz will be the basic counter here. So that is actually 0.1 second in terms of time period, and that is how you generate a time base which is 0.1 second. And taking this as the basis for other counters, we can easily build a 45 second counter by running a count value of 449, always one less here. And earlier in another type of timer we have considered in monoshot, retrievable monoshot, we had considered whatever we program, it used to give the very same time, but in this case it is slightly different because 0 is also reckoned here. So 0 through 9, and we also need another counter for keeping track of 5 seconds, that is what this is doing here. And similarly for 25 seconds there is a case, if you take 215 to 0.1 you get 25 seconds, that is the meaning of this. And one more counter here, and this is the counter which will do the flashing. So for that another timer is required. You can note that, I mean probably we can reuse some of these counters, and I did not reuse just to make it quite simple design. So if you reuse, probably hardware count can be very marginally reduced, so it does not really warrant such exercise. If you want different timings, for example you want to use the very same thing for some other road wherein instead of 45 seconds you need something else, and instead of side road you may have all of them are main roads. So you can very easily amend by just changing these values, that is what this statement says. And we need to invoke the actual design which is traffic controller, and we will have to call it by this module name which you have already seen, and this lists all the IOs here. For example, we have a system clock, then a power on reset here, and these are all just lamps in the traffic light lamps, and MG1 the meaning you can easily make it out. M stands for main, green, and main road 1, and so is the case here for all other. So finally we have a blink as one of the input controls, and towards the end of the traffic the cop normally switches off, or alternately you can have a separate timer which will switch on this based upon the week. I mean day by day it will switch on, of course during the night. And here what we have is a listing of the same IOs here, and from this it is plain for, and all of them are single bit, therefore there is no width declared here. IOs are all declared here, and we also have some assign statements, and all those would demand wire declaration, and that is what is here. This is for advancing the counter, this is a signal to advance the counter. Similarly, to reset the counter I have adapted this nomenclature, and we also need a next value for each of the counters which we are going to use and later on, and that next value is designated by next with the same name as the counter, and the width of each of this counter is here. For example, 22 bits are used for the very first time base, because you had to store a very huge figure of 4 million, and so is the case for other counters depending upon how much time that you need. You can change if you want much higher timing or lower timing, you can always change this bits also. And we declared the registers, that what we have seen as next comes as the actual registered value here, and the same bits happen to be here. And we also have 3 timers basically running, and this can be started by these controls, and they are also reg, because all these reg are appear in always block, especially the clock portion, that is the positive edge of the clock block will be having this all reg, and so also this traffic lights here. So, the actual timer implementation starts here. Counter 1 reg is a free running counter to provide the time base of 0.1 second. We have already seen this for timers 1 through 3. We have 3 timers, and there is one more also, that is for the flashing, and that is not basically a timer, it is only a free running counter. Later on we will see that. And to start with, how we design the first counter, let us have a look. The counter itself is a timer. So, because what it will be apparent, clear to you the moment we cover this. See, first what we do is we increment the counter, it is an advance increment of the counter, so that any computation we will defer it, put it outside the always block, so that during the event of the clock we merely just assign whatever we have computed. All the computation we will do outside and only transfer the contents which will be later on. See, to start with, we have an always block here, a begin and the corresponding end will be there, and it is based upon the positive edge of the clock. Only when a positive edge is encountered, this always block will be executed, and so also when reset pulse is applied, and at negative edge of reset we will have to reckon, and this has been the very standard design we have, you are already familiar with all through the design, this course. And when reset is applied and it is active low, and we need to reset this particular counter, and otherwise, that is else if is for the otherwise. If counter 1 is equal to the time base, what we have to do is it has gone through all the counts, that means. So, we have to only reset back, so that once again it starts going round and round, and that is the statement doing that job. And if not, what we have to do is we have already pre-incremented, so we have merely to assign that incremented value here. So, we do not when the clock strikes, we do not have to start the count, taking the count here. So, it is a good practice, a good design practice to put all time consuming operations outside this always block, because assign statements are always executed all the time, and this is for the time base, and such a simple thing for realizing the counter, and we will see that other counters are also realized likewise. See, except that the timing is different. This is the timer 1 programmed for 45 seconds in order to facilitate the smooth run of the main road traffic, and here what we do is use an assign statement in order to compute the advancing of the counter, second counter. We will advance the counter only if start timer is asserted, and this is 1, and counter 1 is equivalent to the time base. So, that means to say every 0.1 second only we need to take the action. So, only when the count normally it will be advancing from 0, 1, 2, 3 and so on. This when it touches 4 million minus 1, then only this activity takes place. Only then we will advance the counter. And similarly for resetting, it is once again the same pattern, and except that there is this counter 2 is currently running. So, that also will have a load which we have already seen using a define statement, and when it is equal to that load value, and then this is also advancing from 0, 1, 2, 3 and so on. Finally, it will touch the load count, which is the fag end of say for example for 45 seconds we put it as 449 there. When it touches 449 and this is equal to 4 million minus 1. So, then only this counter will be reset, and once again you have an advance increment for the counter, and this is the always block wherein this counter 2 is realized, and once again you have a reset to reset the this particular counter, and also to reset if this condition is satisfied, the condition which we have already seen earlier, and for advancing that condition also we have seen, and it is merely assigning into the counter register here, and thus you have a 45 seconds timer and advance the count once if the timer is still running. That is what the comment says. So, otherwise you do no action, you can just put a dummy statement, no statement at all, or just write the same content there. So, likewise we had to realize timer 2, timer 3. So, I will quickly go through this. It is exactly the same thing, except that instead of 45 seconds we are going to realize only 5 seconds here. This is for the yellow lights, and for the smooth transition while switching from one traffic to another. And this is the advance count. Once again timer 2 will be taken into account here, and as usual counter 1 time base will also be taken into account, because we need to take only when the time base is ripe. And just like counter 2, we have a counter 3 here, and it compares with the corresponding load value, and this is for advance, this for reset. Once again you have an advance increment for the counter and an always block realizing exactly the same thing that we have seen before for power on reset here, then reset and advance condition, resetting here and incrementing here, and this realizes the 5 seconds timer. Once again a dummy statement here, and you have a timer 3, and which is programmed for 25 seconds. It is exactly same as counter 2 as well as 3, and we have an advance counter, reset counter, and satisfying exactly similar conditions, and an advance increment here, then the always block, all precisely the same. There is also a timer 4 or program for 1 second delay used for the blinking of all the yellow lights after the normal traffic hours. So, this is what I mentioned earlier. Here the advance counting is when blink equal to 1, that is a switch there. So, when you say blink, only then it will start blinking, and so corresponding time base once again is taken into account here. And reset is based upon the time base once again as well as the count value, and this, once again it is exactly the same. So, any timer can be very easily realized by very simple counters like this, and an always block as usual with a reset advance, and this gives 1 second timer. So, machine state starts right here. The FSM for the traffic light is here, and once again you have an always block, and considering at positive edge of the clock, and this is our standard format, and you take action if there is a power on reset, in which case you just reset all the lamps. So, all the lamps are here. So, note that all of them are made 0 here. This is for initializing phase, and so also the timers. So that no timer will start without being called for, and we have different states as we have seen in the PowerPoint earlier, S0 through S8 states, and that state is what is defined here as state itself, and this have been defined S0, S1 and so on, and whatever to start with, this will be 0 in decimal and the state will be in 0. When we see the waveform we can understand this clearly. So, in FSM what we are going to do is, once we reset, if the reset is not present, and we will realize a case here, and in case we will have all the S0 through S8 states realized, and if needed we will be examining the blink. Right in the first state we are going to examine whether blink is 1, and if it is 1, take it to the last state S8. In PowerPoint you would have seen that S8 is the last one shown, that is for the flashing of the lights, and it will automatically take, and this query will be made only during the S0 phase. So, no matter when the COP switches, it will only after going through the sequence and touching S0, only then the blink will be sensed. So, it may take, the entire sequence may take 2 minutes, and if you want to take immediately, you may have to incorporate this in every state possible. So, that is not really a requisite, because only towards the end of the day we are going to turn it off. So, that is not really required, this is quite adequate. So, in the first S0 state, the actual lamp turning on or off will arise here. So, if that particular condition is satisfied, so that is a blink, then we do this one, and if not satisfied, we come to the normal functioning here. So, you notice that an if statement is, once it is having executed that one, it will not execute any of this down below, and it will straight away go out of this even out of this case, right. That is the beauty of this if statements. It is a priority quota which we have examined several times earlier, and we turn on the lights. For example, we want main road, there are two green on either ways, and we need to turn them on. So also the side road, because we do not want to allow the traffic for the side road, and naturally we should not forget to turn off all other lamps. That is what these statements are doing. And here if reset counter 2, that is counter 2 is designated as 45 seconds, and if that is 1, that is it has touched the final value, that means. So what we should do is we had to start the timer 1. So here I wonder whether there is a 1 needed here. So we will have a look at it. So may not be required. What state we are in? S0 state, and it goes to state S1. Why should it go to S1? We will have a look. And that is because reset counter is, 45 seconds have elapsed. So with the elapse of that, you need to go to say, did we switch on the timer earlier? No, we did not switch on the timer. Let us see. So we will come back to this. So anyway, we need to go to the second state after the elapse of 45 seconds, and otherwise what we had to do is we start the timer only here. So why is it so? When this is 45 seconds have not elapsed, does it mean? You just verify that. Let us see. So we start the timer and allow it to go to S0 state, that is remain in the same state. So this explains why we had done like that. So if it is we need to start, if it is only in S0 state, this is the very first sequence, we need to start the timer and wait for the 45 seconds to be over. So it keeps on revolving around this, and when it is over, it will take to S1 state. That is what the implication here is. So probably we should have put the other way to avoid confusion, but anyway, nevertheless it does the job. So that is for S0 state. In S1 state, what we had to do is, so we need to turn on yellow lights and red lights and turn off all other lights here, as you see here. And once again, now we check for the counter 3, which is programmed for 5 seconds, and all this pattern will be similar to that. So again we do not start the timer here, but later on, and we will take the control to S2 state after the expiry of 5 seconds. Expiry is coming right at the beginning, and starting of the timer is coming late. So S1 is the very same state. So if you wish, you can always change it, put it before this, then also it should work. So in S2 state, so we need to switch on basically allow the right traffic to flow, and naturally all reds will have to be switched on. So in order to prevent the straight traffic going, and switch off all other lamps. And once again for the next sequence, we check the counter 4, and this happens to be 25 seconds. Once again switch off the timer and remain in the same state, S3 state, and then switch on the timer, and this is remaining in the same state, and S3 is the next state. This is S3, right. So, here we had to switch on all main yellow lights and side red lights. So, side red and main yellow, and switch off all other lamps. And here we inspect for 5 seconds, and once again timer is switched off at this point of time, and control branches off to the next state, and otherwise. So, suppose you wanted the reversal of this, what all you have to do is, if reset counter is not equal to 1, then you can put this group first here. So, that will avoid confusion a bit. So, otherwise we start the timer and remain in the same state S3. All other sequences are exactly same except that appropriate lamps are turned on. So, it is quite FSM realization is quite simple one. You would have noticed that we have started the design without any ASM chart, because it is so plain, simple, direct, and you do not need the ASM chart at all. So, that is the beauty of this particular example at least. And so, this design is quite a simple as well as a small design, and later on we will be looking into the video compression, say DCTQ, that will be a much big, quite a large design, and we will have both the extremes. So, we have seen that red light must be on and side green must be turned this side, I mean at this point of time. So, in S4 state we have to switch on main red lights and green lights, side green. So, that is what it is here, and turn off all other lamps. And once again for next sequence we need 25 seconds, and we check this time counter 4 and start the timer, or stop the timer and remain, go to the next state, or start the timer and remain in the same state. This repeatedly is very same thing that you get. And in this fifth state you need to turn on main red lights and side yellow lights and switch off all other lamps. Once again a 5 second is coming again, and we start the timer or the other way and start it here and remain in the same state, otherwise go to S6 state. S6 is here, and in this case main red and side red lights as well as side right turn lights are turned on. So, this self explanatory, and switch off all other lamps. So, here we have a 25 second, and so once again we go to the next state. If timer is off, then if timer is we make the timer on and then remain in the same state. So, in S7 state we need main red lights and yellow lights as well as side red lights here, and switch off all others. And once again a 5 second delay, which you can just have a glance, and because exactly the same thing we have encountered. Now comes the blink here. This is for the blinking state, S8 state, and so if a blink is on, this corresponds to 5 second timing of timer 2. So, is it correct? I think it should be timer 5, I suppose. So, in this case what we need to turn off all lights except for the yellow lights. So, we have turned off all lights. So, we are going to blink only those yellow lights. So, yellow lights are side as well as main for both directions. So, what we are doing here is we are taking the very same signal and inverting and assigning it to itself. So, if it were 0, it will be 1. Therefore, it will keep on toggling. So, that means it is flashing light here, or what you call blink light, because of the inversion of the same signal. And when should it happen? It should happen when the counter 1 is equal to the time base, that is at 0.1 second time, and counter 5 being equal to the load value of the count 5, and I think I made a mistake there as I pointed out earlier in the comments only something, right. So, it should have been timer, oh, it may be correct, right, it is for 5 seconds, okay. There is something wrong, I must have copied previous comment and not changed this. So, this should be read as 1 second and timer 5, right, rather a counter 5. So, that is the beauty of Verilog design, you can always make a copy from one portion, copy into another. In fact, whatever once the source codes are available, you do not have to key in any of the instructions, you can merely rename this to your design and change wherever your design needs arise. So, that is how you make quick designs. So, here that is what we meant here, and we need to blink only after the lapse of this happening. So, this will happen only when it is 0.1 second and into this 10, this is counter is loaded by 9. So, 0 through 9 it advances, so that means 10 into 0.1 is 1 second. So, every 1 second this will be inverted. So, that means every 2 seconds one cycle is completed, that means 1 by 2, that is 0.5 hertz, that is what we said right at the start. So, if this is satisfied, then having done this remain in the same state, SID state, so long as the blink is still 1, right. If blink is not 1, else will take into effect. So, it will automatically take it to S0 state. So, that is what we said before, blink is also examined in S0 state, we have seen if you remember, and only at that particular state whenever it goes from SID state, it always lands up at S0 state. Similarly, at S0 state alone that blink is examined. So, if your blink is switched on in any other states, so it will be recognized only when the S0 state arrives. So, that is what I said before, if it had just missed when the cop switched on the blink switch, so, and it would take about 2 minutes or so to process that. So, 2 minutes is nothing because the cop is just going home towards the night, right. So, change the state to the first sequence, that is what it says. So, we started with a case, therefore, there must be an end case, and it was in always block, therefore, begin and end, matching end, and we started with a module declaration, and therefore, there must be an end module here. So, as usual, we have simplify results, and we first let us examine the actual outputs here. So, here first, before zooming this output, I will just explain what these signals are. First one is clock, and it is too high a frequency, you can't see the clock because it is in megahertz and we are in the seconds region here, right, and 45 seconds etc. we are seeing here. So, naturally you can't see the clock, and there is also a power on reset here, and that is also of duration 20 nanosecond. So, that gets merged here, you can't see that, and that is these are all the usual signals that we have been used to in several designs before, and this is the blink input here, and it goes high at this point of time, and you can readily notice that some flashing is happening here, and these two lights are yellow lights, MY1, MY2. So, is the case for SY1, SY2 side as well as main. So, that is what we want here, and that is precisely what it is saying. And so, we have a listing of all the lamps, totally 16 lamps are there, main, green, side, red and so on, yellow, red, green and yellow for side, then right, then this is for side right, this is for main right. And here, and before we look into the waveform, let us have a small diversion back to the simplify. Of course, we did not start the simplify, let us have a look at that first. So, in simplify results, so what we had given S0, S1 etc. or this is not part of the simplify, I have overwritten some pertaining to our design information. So, the simplify reports only this here and right up to this, and I have just added this, right, just to make it more clear to you. See what it does is simplify, I mean, is an optimizing tool. So, it normally allocates for FSM states 1 hot assignments, and that is why it has this is state that we had requested, but synthesis tool has made a 1 hot assignment here, and this 0 state corresponds to 1, and this 1 in decimal I have put it here, and all these things are put by us here, and I need to just explain this out. So, 1, then this is 2, 4, 8, you can see follow this here, 16, then 32, all binary update change, and except with the exception of this. In simplify you won't see this here, I have just added here in order to make it clear to you the functioning of this traffic control. So, the idea here is we are going from one state to another, S0 to S1 and so on. After S7 we need to come to S0, then only blink will be recognized, only then it can go to S8 state, which is blink state. In order to explain that, I have put it in this fashion, and these are all standing explained. This last one is 256, and so here when we see the actual waveform, you will see these timings there as 90 microsecond, etc. As explained before, the time base was just limited to 10, and instead of 4 million, because it will be too enormous, we can't have a look all put together. So that it can be confined into single page, so I made it into 10 there. So these are all the timings which we are going to see, and this corresponding time is the actual time that we need is 45 seconds. This 90 microsecond you can interpret as 45, and then you can see this ratio maintain all through. So this will prove that all the counters are working precisely. In fact, only for the very first clock there is a 50 nanosecond error, I suppose, I am not very sure, but as far as the output is concerned, even that 50 nanosecond error is not there. I would recommend that you go through all these simulation signals after back annotation. All these results are once again after back annotation. Back annotation is what we get after gate delays incorporated, and after Xilinx place and route, you have to do back annotation and then simulate. That is what is the real picture, and otherwise you will be mistaken thinking that it will give a high frequency of operation. That is not really correct unless you do the back annotation, as I have insisted all through. And before we go into the details, let us finish the waveform here. See here I will so I have just mentioned that all the lamps are here, the final state is also mentioned here. I will just read out here, I am going to zoom so that you can read it for yourself and verify, and this is state 1, and then 2, 4, 8, 16, 32, 64, 128, then 1, then 256. This is then again 1, because the whole sequence is complete. So this is corresponding to S0, S1, S2, exactly the same thing which we have just now examined in the simplified results, right. So that was the assignment made by the optimization tool, and because it is after back annotation, that will get reflected here, where it merely after simulation, that would not have got reflected, right. So this clarifies that, and we have one more waveform which will also clarify, prove it to you that it is indeed after back annotation, especially the gate delay you can see. So now let us have a look at different states, whether it is doing the right job or not. So in this case, if you examine, I will first zoom here. So you can see MG1, this is the very first state, so it is being high. So anything more than this, what is at bottom you can recognize as 0, and what is on the top of this digit you can recognize as 1, right. You can, for example, this is 0 here. So you can quickly see what here is MG1, 1, 2 as well as side road, all of them are 1. This is the very first state, and all of the other lamps are zeros here, and this is what we want here for the first state, right. So that is what this one is. Then it turns yellow, that is for second state here, that is here. This is small duration, 5 I mean this 5-second, right. So that is here. So unfortunately it is far off here. You can see yellow is turned here, and main green goes low, and side road is still red here. So then what next is I mean S0, S1, S2 state, that is here. So you can see that these two are turned on, that is MRT. Now we had to turn right. So MRT1, MRT2 are turned on, that is at this stage. So then here these are also turned on. So this corresponds to the red, right, say SR1, SR2, that is this here, and all of them, and some more is here, that is MR1 and MR2, these two, they are also turned on. Is this correct? Or probably we looked at the wrong thing, we should look here, right. So only two are there, I think. See, this is not S1, this one, right, and MR1 S and both MR as well as SR MRT are there, and next one is main yellow, side red. Here I mean okay, let us have a look. So that is corresponding to 8, right, that is being yellow light here, and it will be a small signal here. So you can see this here, these 4. So these 4 would mean this SR and MY. Is that what we want? SR and MY, right. So next time it should be MR and SG. That I hope is 16, right, and MR and SG, isn't it? So it is being high only here and here, MR and SG. Yeah. So like this 32 I will leave it as an exercise for you to look into, and what we will do is, and similar so is the case for 64, then once again 5 second, then it goes to 1, and we will examine that blink here, or 1 if you want. So in 1 all are low except for this. So these 2 are there, these 4 are there, that is main, oh that is wrong thing, oh that is one state, right? It is one state, this is what, oh this is 128. So 128 state is S7, so that is this, right. So it is the right turn with yellow there, MR, SR and yellow. So let us see, this is on here, let us see what they are. Yellow, is it, right, and then and 2 more here, that is this MR is there, then should it be one more, MR, S5 we have seen, SR did we see, let us come from SR, then it may be easy. SR is here, SR is 1 here, that the cursor position is precisely that, and then it goes to SI state, that is here, which we have already seen that yellow lights are blinking here, and it is all clean pulse. And in fact, while doing this, I made a mistake in the including the counter. I had explained earlier counter 1 as well as 5. So, I had to take into account counter 1 also. So, I did not take into account. As a result, what happened, there was ringing here right at the rising edge of each pulse as well as at the this edge, right, and that was because this counter 1 is much faster counter, and every time counter 5 goes to 9, counter 1 can be anything. So, for all this that particular frequency clock, that is basically time based. So, that will come through. So, you will be seeing ringing there. It is not really ringing, that is a design flaw. So, be on the lookout for such design flaws. In traffic controller, it may not matter much. Anyway, for control applications like programmable logic controller, etc., that is a very vital thing. Not a single unwanted spike must be there. And this one is, this clarifies the whole thing is working in back annotation, and then it goes to state 1 after this one once the blink is removed, and blink you can see here corresponding to that. Blink is also high here, this is the blink here, and it is withdrawn there. So, you can see right there as blink. So, this proves that the whole thing is working, our design is working. So, we also have one more waveform here. This is just to tell you that after back annotation you have a delay here. So, this is the edge of the clock which is really making it, influencing the outputs. These are all some of the outputs. You can just see the difference in delays here. Can you see the difference? See, this is much ahead when compared to this. This is, both are same, but once again probably even ahead of this. So, you can't really predict how much delay will be in each of these signals, because it has to come through several gates, and those gate delays get reflected as you would see finally when you put it on the FPGA board, make it work, it will be working almost with all this. Although this is a simulated signal, it is back annotated with the gate delays, and that is how it is working here. And before we conclude this design example, let us see the simplify results. So, this operating, we have given 50 megahertz, and so what I have forgotten is, did we cover the test bench? We did not, right? Or okay, we will see later on this. Okay, thank you.